question the quantity this number represents any more than the quantity these objects do. But would you believe me if I told you that this number, in a world without our base 10 number system, could be only 3 of our grapes? Different number bases can be confusing, and it's even harder to understand the connections between them. But what is a base, and how can we use it to create separate number systems? Simply put, our base number refers to the number of digits we use. We have 10 different digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. With these 10 digits and the powers of 10 that each place value denotes, we can write out any quantity in the base 10. But say we wanted to start over and use a different base, like 6. First, we identify the 6 digits we can use. From the 10 we already have, our 6 digits are 0, 1, 2, 3, 4, and 5. Now we learn how to count. We start out normally, but after 5 there is no bigger digit to continue on with, so we shift over to the second place value, that is 10, 11, 12, 13, 14, and 15. Interestingly, in base 6, the written 10 corresponds to what we would put down as 6 in base 10. We can even demonstrate this with the place values, where in base 6 we are grouping numbers by the powers of 6, so our digits are multiplied by the powers of 6 instead of 10. Therefore, a number like 100 base 6 amounts to just 36 in base 10. But what about translating from base 10 to base 6? We take advantage of the fact that our mystery digits are coefficients of the powers of 6, and do division to find them out. When we first divide by 6, we get a quotient and a remainder. That remainder signifies what amount can't fit in any power of 6, so it goes in the first place value, where it would only be grouped by singles. The quotient signifies what amount can be divided by 6, and taking that quotient to divide by 6 again gives a remainder that only fits into 6 and not 36, so it goes in the second place value to be grouped by 6's. We go through this whole process until the last quotient has a value less than 6, since those are the only digits we can use in base 6. And the last quotient goes into the highest place value. This is why the base 2 language of computers is too big and inefficient for us. This number would have 7 digits in base 2. What if we went the opposite route and wanted to use a base larger than 10? We use other symbols, such as the alphabet, to stand in as digits for 10 and greater, which means we can have full-on words be numbers. With the consistency of the place value system, we can write decimals and perform arithmetic operations in other bases too. But why do we bother with other bases? Sure, we're a base 10 society with our hundreds and dollars and metric system, but the existence of 12-inch feet or 60-minute hours rather than 10 or 100 are mathematical relics of previous civilizations, from the ancient Nigerians' base 12 to the Babylonians' base 60. So we're more than just a single base system. From the uses of computers to mapping coordinates to calendars, and applications of different number systems, we are reminded that the universe gave us numbers, but man made the number system.